Section 2.4, the cross product. In this section, we're going to learn about a new operation that takes in two vectors, multiplies them using the cross product, and produces a third vector. That third vector is going to be perpendicular to each of the original vectors. One of the applications of the cross product is to calculate torque, or the amount of rotation that is caused by a force being applied to a lever. And I've got a couple of cute GIFs at the bottom of the screen here to illustrate what I mean. One of the best ones is the one in the center because it really simply illustrates a wrench creating torque on a bolt. You can see that the force is being applied to the handle of the wrench. So maybe you could imagine some force vector being pointed right down the handle of the wrench, and you can see that it's causing rotation. Hopefully you watched some of the supplemental videos that I posted so that you can have more illustrations for how torque is involved in the cross product. But even if you haven't, we're going to get started by looking at some of the mathematics behind the calculations. We're going to start off right away talking about how to calculate the cross product. I've said this before, it's a way to multiply two vectors. And so that's what we're going to do, is start off with two vectors. One vector is called u, the other vector is called v, and we have them written in very general forms at the top of the screen. We want to create a new vector, w, that's orthogonal to each u and v. So I want u to be orthogonal or perpendicular to w. I also want v to be perpendicular to w. So each one of my vectors needs to be perpendicular to this new vector that we create. We know that if two vectors are perpendicular, then the dot product between them must be 0. And so we're going to translate these perpendicular statements into dot product vector statements. And since we know the components of w, w1, w2, w3, wb, no, just kidding, w1, w2, w3, those are the three components for the vector w. And the vector u has components u1, u2, u3. Super generic, but that's useful to point out because if we're saying that the dot product between w and u needs to be 0, we can write that as an equation without vectors. We can write that as a scalar equation, and we can do the same thing for v and w dotted together. Remember, the dot product just says to multiply corresponding components, then add them up. And if we're forcing this dot product to be equal to 0, so that u is perpendicular to w and v is perpendicular to w, then we create a system of equations. I'm going to copy that system right over here onto the right side of the screen because we're going to work with that in just a minute. We're going to take these two equations and solve them just like you would in a linear algebra class, or rather maybe even like a pre-calculus class. We're going to use elimination here. So the first step we're going to do is multiply the top equation by the scalar v3. Now v3 is the third component of the vector v. Why are we using v3? Because it works out. So this is not a way to prove necessarily that the cross product calculation comes this way. It's a way to verify it. So we're going to multiply v3 to the entire top equation. Both sides get a multiple of the scalar v3. And then the bottom equation we're going to multiply by u3. And the reason why we're doing this, again, is to use elimination. So if we multiply the entire top equation by v3, then we can rewrite the equation with a factor of v3 on every term. And then 0 times v3 on the right is still 0. And if we multiply the entire bottom by u3, then we're going to distribute that u3 so that there's a factor of u3 on every term. On the right-hand side, u3 times 0 is still 0. Our goal here is to eliminate the third term. Notice that all of the factors that appear in the third term are identical. We've got v3 times u3 times w3. So these are equal terms. So if we subtract this entire bottom equation from the top, then we're going to cancel out everything in that third set of terms. So let's go ahead and do that subtraction and then write it out. Now I wrote plus 0 because that is like our placeholder for the two terms that were here. I wanted to make sure that we know that those terms canceled out. Next thing I want to do is try to clean this up the best we can. And because I know exactly where this process is going, I'm going to say let's factor out the common factor between these first two terms. And then let's factor out the common factor in these next two terms. And the reason why we want to do that is because it helps us to identify what we need to pick for W1 and what we need to pick for W2 for this equation to be equal to 0. Basically, what we need to do is pick W1 to be equal to the multiplier of W2. So we're going to pick this to be W1. We're going to plug it in right here. And we're going to do the same thing for W2. We're going to use the multiplier of W1. And we're going to plug it in right here. Now, it's true that this feels a little bit hand-wavy, I agree. But the goal here is to find a vector that's perpendicular to u and v. There's many vectors that will satisfy this. We just want to pick one that works. So when we plug in our substitutions here, we're going to see what happens. Oh, I think I forgot to mention we need to use negative to plug in for W2. So I'm going to write negative times u1 v3 minus u3 times, okay. And now you can see that we basically have the same values in the first set of terms and the second set of terms. So those are identical, and these are identical. And because we snuck a negative inside of the W2, we are adding equal but opposite terms, which of course will add to 0. Therefore, we know that the W1 component and W2 component of our system have to be the values that we picked. I mean, they work. Now we just need to find W3. To find W3, we just need to go back and finish the original equation with our substitutions. So if we take W1 and W2 and plug it into either one of the original equations that we found, we can solve for W3. So the W vector that we're looking for will have an x component, or the first component, that looks like u2 v3 minus u3 v2. The y component, or the second component, will look like negative u1 v3 minus u3 v1. And then the third component will be u1 v2 minus u2 v1. So we're creating a new vector that is perpendicular to the vector v, and it's perpendicular to the vector u. And we're creating this new vector using all of the components from u and v. W is the result of the cross product. And the notation that we're going to use for this will look like u cross v. And that's equal to the W that we just found. You're not going to create your vectors using this long system of equations process. I just wanted to convince you that W, in fact, is perpendicular to both U and V, because we started with equations that came from the definition of orthogonal vectors, and then we just did some simple math substitutions to create this new vector W. On the screen, we have a couple different ways to write this cross product for W. In the first line here, we have the standard unit vector notation for the vector W. So if we want to calculate the cross product, we can just plug the components into that version. Or we have the component form, very similar, but we're using the pointy brackets and we're not using I, J, or K. Instead, we're separating our terms with commas. Either way, all we have to do is find out what the components are for U, find out what the components are for V, and then pop them into either one of these equations. So let's go ahead and do it. If we're given the vectors U and V, like what we see on the screen, then we can identify U1 is -1, U2 is 2, U3 is 5, and then V, we have V1 is 4, V2 is 0, and V3 is -3. So we'll plug each of these values into whichever equation we want. In this case, it's not specific about which notation we should use. I'm going to use the component notation because that's my favorite. So when we go to calculate U cross V, we know that the first component is the product U2 times V3, so U2 times V3 minus U3 times V2. So now we need U3 and V2. So that'll be 5 times 0. The second component, we're going to pop in U1 times V3, U3 times V1. And we're going to make sure that this middle term includes an extra negative. And then for the third term, we need U1 V2 minus U2 V1. And then we'll simplify. And there we go. After we've plugged each of the values in, we simplify down and we find the cross product for U crossed with V. Now, if we wanted to reverse our cross product, if we switched it, V cross U, then the order of the terms that we're plugging in will look slightly different. The only difference is going to be that everything is reversed based on the sign. And we're going to talk about this as one of our properties coming up. But V crossed with U, we don't actually have to recalculate it. We just need to change the sign. So it's negative U cross V. It's called anti-commutativity, which means if you change the order of the two things that you're using this operation on, then you have to multiply by a negative in order to keep them equivalent. So V cross U would then be 6, -17, +8. Another way to calculate the cross product in very simple cases is using the right-hand rule. So I've got a picture here on the screen to help illustrate the right-hand rule. We have the vector U, which you start off with your fingers all pointing in the direction of U, and then you're going to curl your fingers. Now, most normal humans, when we curl our fingers, they only curl towards the palm. If you're one of those weird humans where you curl your fingers, but they curl in reverse towards the back of your hand, then this is not going to help you. But for the normal ones out there, when you curl your fingers, the fingertips will curl into your palm. So you're going to orient your hand so that when your fingers are straight, they're parallel to the vector U. But then as you curl your fingers, they're curling towards the vector V. And then after you've curled your fingers, you're going to poke your thumb straight up and that's the direction of the cross product u cross v. So this activity is one that you're going to have to do on your own. Try using the right-hand rule for each one of these problems. I can't really illustrate it without having the video on me, and that's not going to happen right now. So try with your hand, take your right hand, point your fingers in the direction of the I hat vector. And if you ask yourself, where is I hat? Well, it's wherever your fingers are pointing. You're going to set the direction of I hat by opening your hand like you're about to shake somebody's hand. And then you're going to curl your fingers. And the way that you're curling your fingers needs to be towards J. And with our right hand, remember, that's exactly how the right hand rule sets up. So stick your hand out like you're going to shake somebody's hand, and then curl your fingers in towards your palm and stick your thumb up, and your thumb is parallel to the K hat vector. Now for this next one, you're going to have to try a little harder. J hat is not the direction of your normal finger pointing. Remember, J hat with the right hand rule was like your middle finger. So you're going to have to imagine that you're pointing in the direction of J hat and that you're curling up towards the K hat vector. And then whichever direction your thumb sticks out, that would be the result. So what I'd like for you to do is pause the video here, try each one of these on your own, preferably in the privacy of your own home so that nobody thinks you're throwing up gang signs or something. And then check your work. I'll post the answers here, so pause now and then try each one of them and check your work. So once we've worked out each one of these using our right hand, we can then use these results to calculate something a little more complicated. This is a cross product of a cross product. Sounds like cross productception. We're going to use these results to go ahead and plug in what we know for each of these cross products. So if we have I hat crossed with J, which was crossed with K, we can come over to our expressions on the left and find, what is J crossed with K? Well, it's I hat. So we have I hat crossed with another I hat. And two vectors that are crossed with each other, well, heck, if you tried to do a cross product with your hand and you point in the direction of the I hat vector and you curl in the direction of the I hat vector, well, shucks, these two vectors are actually identical. They're parallel to each other. So this actually comes out to be 0. We're going to talk more about why that is in a minute.